Okay, get started. We don't want to miss the lunch, right? So I'll talk about the virtual SVM, shared virtual memory. Like I showed, the full, in the update. What we really want to do with SVM is basically provide this x86 page table to devices. Okay. We have devices, for example, discrete devices, like PCI Express devices, like graphics, discrete graphics controller or FPGA, right? And then some are actually integrated inside a processor package, right? For example, as you saw, the FPGA. FPGA is connected by PCI and then also interconnect like a QPI, okay? So the question is, how we're gonna construct the page table itself is managed by the operating system. And then today, what we have is only the VTD. Then how can we tell the devices that where the x86 page structure, page tables are, right? That's the key question we need to solve, okay? Before that, there are some examples. For example, the OpenCL 2.0 supports that virtual address shared by CPU and the GPU. If we have that kind of the hardware feature, we're gonna see much less latency because you don't need to tell the, hey, for example, GPU, the data is ready, right? Otherwise, the GPU doesn't know where the data is ready. Or if they're sharing some data structure, right, then in terms of programming, it's much straightforward because you need to modify the structure, right? Going back and forth GPU and the CPU. So there are some advantage with supporting SVM. Yeah, this is a picture, and then now this is a little bit complex. It's busy, but it's not so complex as as you see. So today, we have, if we assign device, PCI devices are identified as VDF, device function ID, bus ID, right? So that's this one. And this one is a root table address, it's pointing to this one, and then this is a kind of context table, right? And we use the BDF, again, the bus device function ID as an index in this table, right? And today, there's a pointer for each index entry and pointing to this one. This is a second level page table. You will find why we call second level, but this is basically IOMMU, right? Page table, okay? So what we added, extended was this one, right? So this one is extended to point to first level page table. Basically, this is x86 page table, okay? When we extend it, basically, the extension is coming from a PCIe actually spec. So this is not really Intel stuff, basically with a PCI spec. When the DMA comes with the PASID is a process address space ID, okay? Then if the DMA comes with a PASID, then it points to this PASID table, okay? Then PASID, it will be basically indexed to this, the first level page table. Again, that's x86 page table, okay? So the devices first needs to look at x86 page table that converts the virtual address to physical, right? In a virtualization, it can be guest physical, right? So then again, you need to convert guest physical to machine physical. So that's what we have today, right? This is the IOMMU table. So that converts guest physical to machine physical. So that's the reason we have first and second, okay? So it's not really complex, but we needed to extend, right, to add this table, okay? Now, if you enable this on a bare metal system, okay, that's not so complex, right? You just need to add to support this extended stuff, right? And then make this table and point to the x86 page table. That's it, okay? So it's simple on the native side. If you do this in virtualization, it's a little bit complex, okay? So first thing is, you need to show this BTD inside a guest. So this is a nested BTD, okay? And the complexity is this nested BTD convert the guest physical to, sorry, it's, you know, on the native side, it converts the guest physical to machine physical. If you do this in virtualization, guest physical is not really guest physical, it's virtual guest physical, right? Then convert to the, in his view, converting the machine physical, but it turned out that's a guest physical, right? So this BTD page table is kind of a fake, right? So we really need to have a real BTD, so which is basically this is a shadow kind of page table, right? Now, you probably remember that the complexity with the shadow page table for the x86, right? So one way to implement the shadow page table is, for example, you write protect the page table in a guest, and then you reflect the modification to back to the shadow page table. But that's not really optimal for the BTD because usually guests don't modify the BTD very frequently, usually. But in SVM, it's possible you modify more frequently. But what we are doing is we use kind of a cache. Basically, this is a cache of this one. Because the BTD or the IOMMU has a very well-defined invalidation protocol when you update the BTD. So we use that protocol to sync the virtualize the BTD and then the shadow. Okay, so that's one thing. The other thing is, this is a real one. So the question is, how are we gonna this extended context page table needs to point to the passive table, okay? And passive table in this case is maintained by the guest. So the real one really needs to point to this one because this association is managed by the guest operating system. And we don't want to trap every change to here. So that's the reason we need to kind of map points to this one, okay? So that's the two things we need to do when we're enabling SVM, okay? So anyway, that's a little bit complex, but it's doable, okay? I have more details later, but okay, so this is, again, just complex, but I think the point here is, first of all, we need to expose the capability to the guest, okay, the capability of SVM. SVM capability is exposed in PCI express config space. So it's extended the PCI config space, right? And other thing is, like I said, we use this protocol for invalidation, okay, to sync the virtualized BTD page table and the shadow, okay? So we basically use the queued invalidation protocol, okay? The other thing is fault reporting. So if we use x86 page table, it's possible you get the page fault even with when you use devices. That's not happening today, right? So underlining this BTD engine or IOMMU engine needs to handle the page fault, okay, and communicate that event back to the operating system. And in our case, we need to send that the notification, the events to the guest operating system, because only the guest knows to set up a translation in the guest page table, right? So we really need to get this page fault, it's called a PRQ, page request, okay? And then go back to the guest operating system. Now, one issue with the exposing PCI Express capabilities, because Xen today uses all the chipset, right? This one, Pixie 440, and then in QEMU, it just supports legacy PCI, okay, not the PCI Express, okay. So we need to use Q35 chipset in QEMU to enable PCI Express capabilities, because this SVM is not in the PCI, but in the PCI Express. We also look at the KVM, what the KVM is doing. By default, KVM doesn't use a Q35, actually. It's possible for QEMU to use Q35, but on Xen side, it's not really enabled yet. So we need to work on the QEMU side to make it available for Xen as well, okay? Because if we don't do that, we are missing the new advanced features, not just the SVM, other features are available in the PCI Express side. Okay. So I have more details. So in terms of color coding, the red one means the new code, and then the purple one means the modification. Okay. So this is what we have today. So we have BTD here, right? And then BTD works with the hardware, okay? So that'll be, and then also it can take a fault. So this is start line. And fourth thing is, like I said, we need to extend the QEMU to expose PCI Express features, okay? Those are basically, it's hard to see, but these are page request or SVM features, okay? So once we extend this, we can support SVM features, and then those include, I think, extension to the root address, root table, and then extended, for example, passive table, that kind of thing, and then SVM configuration. Okay. Those are new. Again, the red ones are new code. Okay. Then this one is the IOMMU. Basically, we need to virtualize BTD in guest, right? This way, you get virtualized BTD here, okay? Then this one, I cannot see well this one. Yeah, the queue validation stuff. So this way you can get them sync. Whenever they change, the guest change that the VTD page table, and then need to invalidate using queued invalidation, then we need to intercept that opportunity to reflect the changes to the shadow, okay? And the other thing is the page request. So whenever we get the page forward, then they get the page request and they go back to this one, then we need to inject the page request to the guest, okay? Other thing is the port. So I think the port continues to, if for example, the DMA is go beyond the outside of the protected, the allowed areas, then it needs to generate basically MSI, okay? And then that'll be also need to send to the guest, okay? So those are kind of a detailed change or modification we need Xen, okay? So this is what we have today. I don't think we need to do them, but today what we have is only very high level. Basically, whenever we assign the device to a guest, the device is actually, VTD table is mapped for the entire guest. So we don't really have the nested VT today. So this means that we need to do many things to get virtual SVM in guest, okay? So that's the current status. And we can discuss some more details how we're gonna do that in the design session. So with that, I think I'm done.
Okay, good. Yeah, we're now 3 minutes over, but that's fine. Lunch, I guess, has started. So as you say, the design session's this afternoon. I think it's at 3:20 for this one?
Yep.
Okay, thank you.